All right, good morning. This is Mr. Smith. This is Algebra 2. We are now in the second part of the course, the downhill stretch, you can hope. Section 6.1, evaluating nth degree roots and rational exponents. So we have seen linear equations. We've learned how to solve them and graph them. We've seen quadratic equations. Learned how to solve them and graph them. We took the next step then to polynomial equations. We learned how to solve them and graph them. And now we're going to venture into the next realm of rational exponents and radical equations, and we're going to learn how to solve them and graph them. Okay, so that theme, solving and graphing, does not go away in algebra. And so the first idea that we want to talk about is this idea. If I have, for instance, 2 to the third power, this is 8. But if I want to undo this, let's say I start with the 8, and I want to get back to the fact that I took 2, right? So this would be considered the cube root. Right? So in the same way that we have, I can square something and then I can square root it. Right? Those are opposite processes. I have the idea that if I cube something, then I can cube root it to undo it. Okay, so that idea should be something that we're a little bit comfortable with. And so the first, if I can divvy this up into sections here. All right, so the first idea is talking about the nth root of A. Okay, and so in this section, we're going to use any root. So we could use the third root, the fourth root, the fifth root. We're not limited now to what root we're going to look at. Okay, so we've looked at primarily before this square roots and maybe occasionally a cube root. But in this section, in this chapter, every root is now in play. So we may be taking fifth roots. And by the end of today's lesson, we will be. Okay, fifth roots. Okay. The next idea is that I can write a root as a fractional power. Okay, so we can write roots as fractional powers. So, for instance, if I have the square root of A, notice it's square root, we don't write the 2 here, then we can also write that as A to the 1/2 power. Those two statements are equivalent. Namely, if I take the square root of A, it's the same as A to the 1/2 power. Okay, if I want to talk about the cube root of A, so you throw in the 3 here, cube root of A is the same as A to the 1/3 power. Okay. Talk about the fourth root of A. That's A to the 1/4 power. So up until this point, all of our exponents have been integer values. After this point, we can now work with any exponent, whether it's an integer or whether it is rational, whether it could be a fraction now. Okay, we now have a meaning for A to the 1/2 power is the same thing as the square root of A. And what you see here is that, for instance, if I take A to the 1/2 power, so the square root of A, and I square that, right, those two processes should undo each other. If I have A to the 1/2 power and I square it, those two processes undo each other, and it just gives me back A to the 1st power. If I have A to the 1/3 power and I cube it, right, so cubing and cube rooting, those two processes should undo each other, and they should give me back to A to the 1st power. Okay. Likewise, A to the 1/4 power, and I take it to the 4th. I take that to the 4th power, or I take the 4th root of A to the 4th, right? That gets me back to A to the 1st power. Those two things undo each other. Okay, so there's 3 things to see on this slide. Number 1, any nth root is now in play. Okay, we can take any nth root of any number. Okay. Number 2, we can write a root as the same thing as a fractional exponent. Okay, so A to the 1/2 power is the same thing. It means the same thing as A, and we take the square root of A. Okay. And the third thing is that these processes undo each other, so squaring and square rooting Squaring and 1/2ing are processes that undo each other. Okay, so 3 things to see there. The next idea splits up even roots versus odd roots. Okay, the way that we handle even roots and the way that we handle odd roots is slightly different. So, if n is an even root, if we're going to take an even root, square root, 4th root, 6th root, and so forth, then we have 3 different cases. So for instance, if we take the square root of -2, so if I take a square root of a negative number, there is no real solution. Of course, we've worked on what the imaginary solutions are, but for the moment, let's just rest with no real solution. If I take the square root of 0, it's just 0. And if I take the square root of 4, it is plus or minus 2. Okay, so the idea here is that there are 2 solutions, namely 2 times 2 is 4, -2 times -2 is 4, and this is going to happen with any even root. So it doesn't have to just be square root any longer. It could be a 4th root, or a 6th root, or a 10th root. Okay, we'll still get 2 solutions, and this is what tells us that. Now, if n is an odd integer, so we're taking an odd root, like a cube root or a 5th root, then, so let's, for instance, take the cube root of a -8. Here, we're allowed to take cube roots of negative numbers. Right? If it's an even root, we get no real solution. But if we're taking an odd root, cube root of -8, the answer is just -2. And the reason is because -2 times -2, positive 4. Positive 4 times -2, -8. Okay, so that works. Cube root of 0 is just 0. And the cube root of a positive number like 27 is just 3. There's only one solution there. There's only one solution there. Cube root 27 is just 3. Okay? So we need to pay attention to whether or not we're taking an odd root or we're taking an even root, because our results will be affected by that. All right. So let's see a couple problems in action here. Let's get a couple under our belt. So here we go. Find the indicated real nth root of A. So they say we're going to find the 3rd root of A, where A is -64. So cube root of -64. Cube root of -64. And this will be just -4. The reason is because -4 times -4 is positive 16, but positive 16 times -4 is -64. Okay. Cube root of -64 is -4. Now here, for part B, they want us to take the 6th root of 729. Okay. So it's the 6th root of 729. By the way, we have a new way that we could write this. Right? We can use that fractional exponent. So 729 to the 1/6 power. Okay, those are the same. That means the same. We could have done that over here. Right? I could have put -64 to the 1/3 power, which equals -4. Okay. All right, these two notations, 6th root or some number to the 1/6 power, they mean the same thing. And now we need to figure out what number times itself 6 times is 729. It's probably something pretty small. Any takers? What do you guys think? Tyler, what do you have? Okay. Looks like maybe 3 to the 6th power is 729. 3 to the 6th powers. So the answer here is The answer here is plus minus 3. And you should verify that, right? 3 to the 6th power, 729, 3 times 3 times 3, all the way out, gets us there. But negative 3 also will do that, right? Because negative times negative will be positive, negative times negative will be positive, negative times negative will be positive, and we'll have a positive 729. Okay? And also, this last slide tells us that if we're taking an even integered root, I expect 2 cases. Okay. All right. Are there any questions there? Okay. All right. So let's take a look now at building this a little bit more. So now I don't just want to take a to the 1 over nth power. It's a little basic. Let's expand it now, and we're going to take a to the m over n. So basically we could have any fraction be an exponent. A to the m over n, where any fraction could be our exponent. And what we do is we break it into 2 pieces. We first consider a to the 1 over n, and all of that to the mth power. Okay, that's the way that we handle these problems. Okay. So we break it into 2 pieces where we take, if I have a to the m over nth power, then we consider it as first a to the 1 over n, and we can evaluate that, and then whatever that is, we take that to the mth power. And they also show us what to do if it's a negative m over n. Okay. If it's a negative m over n, remember, anytime we have a negative exponent, that just takes our base, and if it was in the numerator, brings it to the denominator. If it's in the denominator, brings it to the numerator. And so here you can see them shifting because of the negative exponent here. They shift a down to the numerator, out of the numerator into the denominator. And now they break it apart just like they did above. All right. And so again, let's take a look at a few examples here. All right, so here we have 16 to the 3/2 power. 16 to the 3/2 power and 32 to negative 3/5 power. Okay. So 16 to the 3/2 power, we can break this up into 16 to the 1/2 power, and then that cubed. So 16 to the 1/2 power is, so what we have to think about, what does 1/2 power mean? So the 1/2 power should be the same thing as square rooting. Right, so 16 to the 1/2 power should just be 4. 4 cubed is 64. Actually, let me rewrite that. So I show the 4 cubed. All right, so 16 to the 1/2 power is 4, and 4 cubed, there we go, 64. Okay, so we break it into 2 pieces. We break the fraction into 2 pieces, and now we go from there. Go ahead, Don. It's a great question. And if you want to consider that here, you can. The plus minus piece will more come out when we're solving equations. But I agree with you 16 to the 1/2 power is plus or minus 4. So maybe we break this off and we say, well, this is plus 4 and this is say the again. Certainly seems like it should be. The plus minus piece will really come out when we're solving equations, like I said. And at some point we'll restrict. I'll tell you don't consider this case. But if I don't tell you not to consider it, I mean, right? 16 to the 1/2 power. We just addressed the idea that this is an even root. We should get two solutions, plus minus. So in that sense, yeah, let's keep it. Go ahead. Right. So 16 to the 1/2 power, right, is the square root of 4. Sorry, is the square root of 16. This piece right here. That's right. You take this piece and then you cube it. Okay? And we'll see it again. Let's do 32 to the negative 3/5 power. Okay? So the first thing I want to do is I want to work with the negative exponent. So negative exponent says whatever this was, if it's in the numerator, take it to the denominator. So it's going to give us 1 over 32 to the 3/5 power. And now we're going to break that into two pieces. So this will be 32 to the 1/5 power, and then all of that cubed. Okay, so 32 to the 1/5 power. It's literally saying there's some number times itself 5 times that equals 32. What is that number? And so in this case, that is 2. 2 times itself 5 times gets me 32. So the 5th root of 32 is 2. And now I'm supposed to cube that. And so we get 1/8. So 32 to the negative 3/5 power is 1/8. Okay. Let me pause here for just a moment. Okay, so at this point, we're going to look at some equations. And we're going to try to use our rules, our properties that we've been developing so far this morning to assist us here. Okay. So we've seen something very similar to A as long as it was x squared. Right? If I had 4x squared equals 128, I think most of you would have no problem solving it. And probably most of you are pretty good on this. But let's talk through. What could be an approach here to start going? Go ahead. So we if this said x squared, we'd certainly want to be talking about square roots. Okay. Go ahead. All right, so let's get rid of the 4. Okay. So x to the 5th equals 32. X to the 5th equals 32. And now how do I undo x to the 5th? That's the idea of what this section is trying to get at. And so to undo x to the 5th, we can raise it to the 1/5 power, right? X to the 5th to the 1/5. That undoes it. Both parts undo each other. Or we can think of it as taking the 5th root. Either way. So for the first time, I'll write this as x to the 5th power, all to the 1/5 power. And if I raise the left side to the 1/5 power, I have to raise the right side to the 1/5 power. Taking something to the 5th power and then to the 1/5 power, those cancel each other out. leave us with, it's right over here, x equals 2. 32 to the 1/5 power is 2. If it's an odd root, if I'm using an odd root, there's only one piece. Okay? It comes back to that slide, even or odd. Okay, so we'll have to pay attention to that. Now, in part B, careful, some of you may want to try to multiply this out, x minus 3 to the 4th power. But remember, if you really multiply that out correctly, you're going to have to do x minus 3 times x minus 3 times x minus 3 times x minus 3. And that's not going to be fun. And that's not the approach we're looking for here. What I see is I have x minus 3 to the 4th power, and I want to undo this. I want to undo the 4th power, so we take the 4th root, or we raise it to the 1/4 power. And this time I'll write it as the 4th root, so like this. But remember, if I take the 4th root on one side, I have to take the 4th root on another. And also, because I'm taking an even-powered root, I need to consider both the plus-minus case on the right-hand side. And so what happens over here is I take the 4th root of something to the 4th power. Those cancel out. And that leaves me with the 4th root of 21. Now, there is no integer value times itself 4 times that gives me 21. So for right now, we're just going to leave it like that. I have an x minus 3 on the right-hand side, so to get rid of the 3, I add it. And this gives me my 2 solutions. 3 plus the 4th root of 21, 3 minus the 4th root of 21. If you want to consider this as a decimal, you can. If this had worked out nicely to be an integer value, then of course I want you to go the next step in whatever 3 plus that number is, do that, 3 minus whatever that number is, and do that. Okay? So here are two equations where we're using our understanding of exponents, rational exponents, to help us out. All right, so here I have 2 more problems for you that mimic those last 2. Why don't you try these? If you're watching the video, if you pause it and work on these problems, and then when you resume, we'll go through the answers. You may pause now. All right. So here, to get rid of our cubed power, we're just going to take everything to the 1/3 power, or the cube root. In this case, I'll write it as the cube root, and the cube root of negative 14. And so here we get x minus 2 equals the cube root of negative 14. We add the 2, x equals 2 plus the cube root of negative 14. And there's no number times itself 3 times to get to be negative 14. So we can just leave it like that. Notice there aren't 2 solutions here. There are not 2 solutions here because we're taking an odd-powered root. For example 18, we are going to take the 4th root, or take everything to the 1/4 power. So this is x plus 5 to the 4th, and all of that to the 1/4 equals 16 to the 1/4. And so this, over here, the 4th power and the 1/4 power cancel out. It leaves us x plus 5 equals 2, plus or minus, right? 2 to the 4th power is 16, but we need to consider both cases. We subtract the 5, x equals negative 5, plus or minus 2, and we should evaluate this now. X equals negative 5 minus 2, negative 7, and x equals negative 5 plus 2, negative 3. 2 solutions there. Okay? Let's take a look at one last problem, and we'll be finished for the day. So here it is. Okay, so why don't you work on this at your seats, work on this at home, and see what answer you can come up with. Okay, go ahead. Okay, so if you do all of the work down to the second to last step, so we subtract the 350, we divide by the 3, we should get x to the fifth power equals negative 243. So now I'm going to take the fifth root of this, right? So I take the fifth root on both sides, or raise everything to the 1/5 power. And in this case, fifth power and 1/5 power cancel out, and negative 243 to the 1/5 power should be negative 3. Okay. Because it is an odd power, there should only be one solution, and that is to say, if you take negative 3 times negative 3 times negative 3 times negative 3 times negative 3, you will get negative 243. Okay. So this concludes section 6.1. Thanks for your attention. Have a good day.